First of all, I didn't discuss how we find out these unstable modes. But finding these unstable modes are not a trivial business. We use a method that are proposed first by Benedin to compute just the exponents or the corresponding eigenvalues, if you like that analogy. And also generally to compute the corresponding covariant vectors or the eigenvectors, if you like the analogy. The method is very similar to Paul iteration, if you're familiar, to find out the eigenvalue-eigenvector pairs of a matrix. And that's starting from random initial conditions. So that is what I have you look at the video here, is that because we start with random initial conditions, initially it has a lot of noise in the computed covariant vectors. And only after a while the noise gets washed away, and you can only prove that you converge to the right answer after infinite time. Okay? So what is the error as a result of this noise or inaccuracy in the computed modes, in the computed sensitivity, or how to estimate how much error is there? I think it's more like a low-hanging fruit because there is an analogy from Paul iterations to use. But are there ways to estimate them cheaper or more accurately? This is really a central question that is a lot harder. And how does the error affect the sensitivity analysis method that rely on computing these unstable modes? Okay, and a related challenge is there are just too many of these growing modes in 3D chaotic flows. For example, this is one of the cases we presented in our paper that has 12 unstable modes. It's a two-dimensional backward-facing step that is computed using OpenFOAM. This low-pressure turbine, one of the lowest Reynolds number three-dimensional flows we can compute that has an industrial application there, has almost 500 unstable modes. We expect that when we go out there and look at more applications, probably we will have cases that has a lot more than that. How can these modes be computed faster? It's really an open question. We are investigating ways to maybe we can get multiple modes out of a single solution of the linearized Navier-Stokes equation, and to explore not just the simulation as just an ODE, but really starting to look at the turbulence as a spatial temporal chaos. I think is the right direction to go on here. And also, is it possible to not having to compute all of the unstable modes? So one of the ideas is in computing, in solving the linearized or adjoint Navier-Stokes equations, can we inject local viscosities to remove the unstable modes that we may not care that much, like all the small scales, and only look at the important ones?